Hello students, welcome to lecture number 2 on operational amplifier. In this video, I will discuss 3 different topics on operational amplifier. Number 1, characteristics of an ideal op-amp. Number 2, differences between the ideal op-amp characteristics and a practical op-amp characteristics. Then move on to number 3, and that is the ideal voltage transfer curve of an op-amp. So let's start the video. So number 1, ideal characteristics of an op-amp. This is the first point, that is infinite open loop voltage gain. Carefully notice the term open loop. So when an op-amp is in a closed loop, that is when a resistance is connected across its input and output terminals, it will be an closed loop configuration. But this point tells us about the open loop configuration, or whenever an op-amp is in open loop mode, then the voltage gain is infinite. Number 2, infinite input impedance. What does it mean? If the input impedance of any device is infinity, it means that no current will enter through the device. For an op-amp, if the input impedance is infinite or infinitely large, that means any signal source can drive this device. Third point is zero output impedance. Now, if any amount of current enters into the device and then it finds that the output impedance is 0, it means that the entire current will flow across the device, or it will move out of the device. So there will be no current loss inside the device. Now for an ideal op-amp, this output impedance 0 means that the op-amp can drive an infinite number of devices. Okay? Next, number 4, that is infinite bandwidth. That means that any signal ranging from frequency 0 Hz to infinity Hz can be amplified by an op-amp without attenuation. Now the next point is perfect balance. That is, the output voltage of an op-amp will be 0 if equal voltages or 0 voltages are applied at the input terminals. Now let's elaborate this point further. For an op-amp, there are two input terminals, as we know, that V1 and V2, where V1 is the input voltage of the non-inverting terminal and V2 is the input terminal at the inverting terminal, and let's say it as V0. Now if the gain of the op-amp is A, then the output voltage expression will be equals to A into V1 minus V2. So as you can see that if V1 equals to V2 equals to 0, or if V1 equals to V2, then V0 will be 0, and that is the point expressed here, that is known as the perfect balance. The next point tells us about the temperature dependence of an ideal op-amp. It tells us that characteristics do not drift with temperature of an ideal op-amp. Now the 7th point is also an important parameter for an op-amp, and it is the common mode rejection ratio, that is in short CMRR. And for an ideal op-amp, the value of the CMRR is infinity. It means that it will reject the common mode voltage gain. Now CMRR equals to AD by ACM. AD, where AD is the differential voltage gain. Differential voltage gain means that when the difference voltages are applied at the input terminal, and whenever equal voltages are applied at the input terminals, then the gain is known as common mode gain, and CMRR is given as AD by ACM. Now as we know that from this fifth point, that is whenever equal voltages are applied, the output voltage will be 0. That means for equal voltages applied or the common voltages applied at the input terminals, that ACM should be 0. So for an ideal op-amp, the value of the CMRR will be infinity. And now last but not the least, that is point number 8 tells us about slew rate. And for an ideal op-amp, the value of the slew rate is infinity. Now again, what is slew rate? Slew rate is actually means the rate of change of maximum output voltage for an op-amp. So slew rate is given by dV0 dt max. dV0 dt max. Now for any device, we require that whenever a voltage is applied at the input terminal, we should get a instantaneous output voltage. So we are interested about dt, and that dt should be small enough or it may be equals to 0. So for an ideal op-amp, the value of the slew rate should goes to infinity. Now in this second part of the video, I will discuss characteristics of a practical op-amp. Let's start. So the voltage gain for an ideal op-amp is infinite, but for a practical op-amp, it is about 10 to the power 3 to 10 to the power 6, quite a large value. Input impedance, the value of the input impedance is also about 10 to the power 3 to 10 to the power 6, but not infinity. And the output impedance for a practical op-amp is about few ohms, typically around 75 ohms. Now the bandwidth is obviously finite. The voltage gain is constant up to few kilohertz of frequency, and then the gain will decreases. Point number 5 and point number 6, that is for a practical op-amp, it is not at all a perfect balanced device, neither the characteristics do constant with temperature. So characteristics certainly change with temperature, and the device is not at all a perfect balanced device. And then the value of CMRR and slew rate, obviously these are not at all infinite, these are all finite values. So this is a comparison between the characteristics of an ideal op-amp and a practical op-amp. So let's move on to our third topic, that is the ideal voltage transfer curve of an op-amp. So this is the ideal voltage transfer curve of an op-amp. Here this is the output expression for an op-amp, and this is V0 equals to A into V1 minus V2. Now this V1 difference V2 is known as the input difference voltage or VID. So in short, V0 can be written as A into VID. Now here in the ideal voltage transfer curve, we plot this VID versus the output voltage. As we can see that when V1 equals to V2, that is VID equals to 0, then V0 should be 0. So this is the point when VID equals to 0. Now as the gain of an op-amp, what we have earlier discussed, that for a practical op-amp it is actually about 10 to the power 3 to 10 to the power 6. That means for a slight value of the input voltage, V0 should go to a large value, and that is the Vsat value. So for VID positive, although it may be a very small or a very little value, but this will transfer, or this will bring the output voltage V0 to a large value. But as the biasing voltage, that is the positive biasing voltage, is plus 12 or it may be maximum plus 15 volts, so V0 could not cross that maximum value of plus 12 or plus 15 volts, and that is the positive saturation voltage. So for a slight increase in input difference voltage, so for a slight value of VID, the output will quickly switch over to the positive saturation voltage, and it will remain there. It will constant throughout as you increase the value of VID. And similarly for VID is a negative value, that is VID is negative, the output voltage also switches to the negative saturation value, and here also the negative saturation value is, as you know, minus 12 volts or maximum minus 15 volts. So the output voltage will stay there at minus 12 or at minus 15 volts. So this is the ideal voltage transfer curve for an op-amp. Now if you find this video helpful for you, please give me a thumbs up. Till then, goodbye.